So this discussion of solving a set of linear algebraic equations is in the context of finite difference methods and finite element method. Those methods lead to linear algebraic equations and mostly very large set of linear algebraic equations. So how do we solve them? In the finite element method that we developed earlier in a separate video, we showed that the equations for two adjacent elements, so two adjacent elements meaning it's two elements having, these are 1D, so there are three unknowns. So T1, T2, T3, so it's like this, 1, 2, 3. So there are three unknowns, and so for three unknowns we developed these three equations. This was shown earlier, and again it's in a separate video. Now, of course, you all know how to solve this one, okay? But just remember that this equation is being solved at every time step, meaning you take another time step to march in time, you have to solve this equation or some version of it again. Okay, so in a complex domain and complex physics, even though what I'm showing here is 3, in such a complex situation, 1 million is not that uncommon. So 1 million, if we try to do exactly what we are doing with this 3 by 3, it's going to have trouble. And so we have to look for doing it more efficiently. We have to look for solving these large sets of equations more efficiently. So study of linear algebraic systems is a subject by itself, and study of efficient computational approach for linear algebraic systems is also an area. And so we are obviously not try to even scratch the surface, because we're going to spend about 10-15 minutes to talk about the ways to solve this. So we just want to be aware of the two different groups of methods. That's all we will do. So there are two general groups of solution methods. One is a direct method and the other one is indirect. And so in direct methods, we solve the equations exactly, and the characteristic of it is it needs more memory. And we're going to talk about an example of this direct method. So it can run out of memory for very large systems. That is one disadvantage. And in some cases, round of error can be a problem. So direct methods are exact, but we have some issues with it. One of the many methods that we'll cover is Gaussian elimination. Indirect methods or iterative methods, on the other hand, are good for large and sparse systems. So what is a sparse system? So this finite difference and finite element methods lead to matrices that have a lot of zeros. So here is the one that we derived in FEM, a finite element method, and you can see all of these elements here and here, they are zeros. Okay, so when we have a lot of zeros, of course the characteristics of solving that is different, and indirect methods turn out to be more efficient. It is likely to need less memory, and it can reduce round of errors. One of the many methods that we'll cover is the Jacobi method. So now we'll get to the details of two examples, one from each of these direct and indirect methods. So we will go through an example of a direct method now. Here is the equation we start from. This is the one I just showed in the previous slide. And this is something all of you have solved. It's three equations with three unknowns. But let's go through this process in a somewhat systematic way. So what we want to do is use the first two equations, use the first one to eliminate one variable. We will eliminate this variable, so then we will transform the second equation into one having only two variables. And then we will have two equations with two unknowns, T2 and T3, and then we can solve it, or in a way we can repeat the process until we get to just one unknown left. So let's do this process. It's easier to just do it. So the first equation, that if I write the equation here, write out 3t11 plus 0.0017 T21 is equal to 0.1843. I multiply this entire equation by a 0.0017 and divide by 0.0033. So if I do that, then look at this guy, this coefficient. If I divide by the same and then same number and then multiply by 0.0017, then I'm going to get 0.0017 here. And then I take that equation and subtract from this one. So if I do that, because this is going to become 0.0017 after all the work, and then that equation, if I subtract from here, then I'll get a 0 here. Okay, so it's going to look something like this, not something like this. It's going to look like this. So now what did we do? I eliminated this term. So I eliminated T1. That's why we have a 0. And so again, so now we have two equations with two unknowns. And then we kind of repeat the process. Okay, so now we repeat the process with these two equations. So from these two equations, we are going to try to eliminate the T2 from the last equation. So if we eliminate T2, then we're left with only T3 for that. So we can solve for T3. So how do we do that? So if you take the second equation, T21 plus T31 is equal to 0.2751. Now multiply and divide this equation. So I divide it by 0.0058. So this will give me 1 here, and then I multiply by 0.0017. So I'll get 0.0017 here. And so this will give me 0.0017 T21 plus other things. We don't need to do all of them in the video here. And so I take this equation, I subtract that one from this equation. So you notice this equation has 0.0017 t21, and then this has 0.0017 t21. So this will become 0, and so we will get this matrix. So this is the 0 that we got. So now we basically have solved it, because now what we can do is from this last equation I can find T31 is equal to 0.147 divided by 0.0028. So I know T3. So if I know T3, then I back substitute. So this equation has T2 and T3. So if I substitute for T3, then I get T2. And then with T2, I back substitute here till I get T1. Okay, so I know T1, T2, T3. So that was one method, and a software can implement one or more of these methods. So I happen to have a snapshot from the software COMSOL, which implements these methods as their direct solver. So this is their direct solver. This is their solver configuration, direct solver, and these are the many different direct solvers that they have implemented, and they always have something as default. Okay, and so how do they get the default? They do partly based on experience and partly based on theory, what works for a certain type of physics, certain size of problems, and so on. Now, each one of these direct solvers, there's a major amount of work that goes on. So for example, this Paradiso is a project by itself. Okay, so this is a project that lots of people are working on in trying to make things faster and more robust. And another question is, we have these default, and then if we need to tweak, because sometimes things don't work, then we need to tweak. How do we know how to do that? For that, I'm afraid there is nothing else other than practical experience, and these are typically cataloged in their user group communications for a software. So different people share their experiences, so you have to go through, one has to go through those experiences to see what might work in a given situation. So this is very practical. There is no other way to do this. So I really meant it, that there is no other way to do it than just from practice. So just to make the point, I have copied here a direction from the software COMSOL multiphysics, and as we could guess, they're saying several direct solvers are available within COMSOL, and they're saying either Paradiso or MUMPS are likely to be the fastest, and spools will likely use the least memory. So this is a very general guideline. Okay, so there are very few universal guidelines, and so these are a few that you can see. So they're saying all should converge to the same answer. and the dense matrix solver should only be used for some special type of a numerical method called boundary element method. And so again, you see that we do not have universal guidelines. And this is the best that we can do. Quite often, as I will repeat again, quite often the default solver is good enough. The other group of method is indirect method. The one we just finished is direct method. Indirect methods are iterative methods, are used for large and sparse systems, that they are more efficient. They are likely to use less memory, and they can also reduce round-off errors. We are going to do one of those many methods, one called the Jacobi method. So instead of the direct method that we just did for solving these three equations, so these being the unknowns, what we did in the direct method is using these two, we eliminated this one. So then we made this equation as two variable, and then with a similar process we made this one as one variable, and then we went back. So this we manipulated in a very direct way by substituting one equation or some version of it into another. Instead of that, we're going to do things iteratively. So we take these same equations, so those are the three equations that are shown above in the matrix form, and I'm going to write them this way. So from the first equation, I write T1. So I take this to the other side and then divide by 0.0033. So that's how I get this one. So I just rewrote T1 in terms of T2. And I do the same with the second one. I write T2 in terms of T1 and T3. And then T3, from this equation, I write in terms of T2, okay? So just because we wrote it this way doesn't mean we can solve it, because these guys, T1, T2, on this side, there, and T3, all those are my unknowns. So the right-hand side is unknown. So how do we go about this? So in this process, we try a guess for all of these unknowns. Okay, so we take a guess and then we plug in the guess. Okay, so this is our guess that we plug in here, and if we do that, then all of these can be computed, and from there therefore I can get T1, T2, T3, which is kind of my improved version. And hopefully it does improve, and in general it does improve. And so we take that, the new calculated value, and in my next iteration I plug them back in here. Okay, and so I keep doing this until what I plug in here is pretty much what I get back in here. So I plug in from here and then I get back about the same quantity. That's when we say this process has converged. So we're going to just try out that iterative process, plugging in actual data. So nothing really difficult. We just want to do the actual number crunching. So here is the iterative solver that we have, and we have to plug in some initial guesses for the variables on the right hand side, and that will give me some improved guess for the left hand side. So what would be a good guess for the right hand side? This can come from many different sources. It may not even possible for us to have a very good initial guess, and that's not where this method depends on. This method does not depend on a very good initial guess. So in this case, I chose, because it was a heat conduction problem in a slab, transient heat conduction problem that has a initial temperature given, and that initial temperature I thought would be a good initial guess, because if it's a heating cooling process, it is likely to stay somewhere close to that, especially in this bio application. But it may not be possible to do this kind of a guess based on physical insight always. So in this case, I use the initial temperature. So that's what will go into the right hand side, and that will give me an improved left hand side. And so the improved left hand side would be these values. This is what I will get by doing the computations here. And I repeat the process. Then I take this and then plug in here, and that will give me the next set of values. And we keep doing this. Now, if we decide to let's say we're going to make sure, let's say, that it matches till 3 decimal places. So you can see after the 8th iteration, the 3 decimal place convergence has not reached. And so we keep going until, let's say, 15. And then by then you see the 3 decimal, up to 3 decimal places, they're kind of the same. So which means we say that the iterations have converged here, and so this is my solution. And this, how many decimal places and so on, we don't get into these kinds of details. These are already fixed and set in the software. Yes, they already have a default value in the software. If we need to tweak, yes, we can, but many times we don't need to tweak these, and the process ends in some sort of a converged value. So here is an actual snapshot of choosing an iterative solver from one of the software. This one happens to be for COMSOL. And so under iterative solver here, when we click that, we get this page, and you see this is a drop-down menu. So there are more than one choice. There are several choices for iterative solvers, and for the type of physics and everything else that was chosen, the default solver happens to be this GMRES. It could be a different one for a different problem. And you see some obvious controls that we have. For example, a number of iterations before restart. So they have some default value, and maximum number of iterations. So we don't want the program to be just going forever. So there's an absolute maximum number of iterations at which after that it stops if it had not reached convergence. So here is a page that I showed you first for direct, and now I'm showing for indirect, copied from the company's software manual. And just like for the direct methods, there are going to be several iterative solvers available, but there is no sort of one solution that is perfect and that is known beforehand, generally speaking. So when an appropriate solver is known for a particular problem, the software will automatically present that combination as an option, and the best one would be there as a default. But it's important to know that there are multiple solvers available, and there is nothing to say, oh, this is obviously the best one. And also they are saying manually choosing an iterative solver and adjusting all the settings inside the solvers, as I showed you, is not usually advised. So we basically leave it at default, and if that doesn't work, then we have to carefully look into it. So now, to summarize in terms of choosing a solver, it's kind of easy because there isn't as much we can do. But generally, there are two different classes of methods. So those are the direct solvers and the indirect solvers. So those are the two different classes of methods exist, and there are many choices within each one. And depending on the method that we choose, the memory requirement and speed is going to vary. Okay, it's important to know that there's very few general guidelines. Okay, whatever is generally known is generally built into COMSOL as default or any other software that we are using. But in general, it is hard to guess, exactly which kind would give us the most accurate and the fastest solution. For small sets of equations, many of our typical small problems that do not have a lot of physics, not a huge geometry with lots of elements and so on, it is not critical. It is not critical to choose a solver. So choosing a solver is not that critical. We can just use the default.